This is our submission for the Duke CS Undergraduate Showcase. My name is Sriram Gollapudy, and I'm joined here by fellow undergraduates Kush Gulati, Jason Lee, and Angikar Ghosal. The aim of our project is to more intelligently schedule courses here at Duke University.
First, a little background on how we became involved with the project. We are all members of Duke Applied Machine Learning, or DAML for short. DAML is a student organization focused on building, implementing, and deploying end-to-end machine learning models to solve research and business problems. One of our members was contacted by a faculty member regarding course scheduling here at Duke, as the faculty member had been involved with scheduling prep courses prior and had heard of other institutions optimizing their course scheduling through machine learning, although they had not specified how. DAML was then tasked with the project, and eventually our client became the Duke Registrar's Office, who supplied us with data and resources.
To provide more specific context, we learned quickly that scheduling courses at Duke was done primarily intradepartmentally, and that there was little data available on how often courses not offered by the same department may be correlated, i.e., how often students would try to take both courses in the same semester, or on how often two courses may have been offered. This results both in suboptimal student schedules and in suboptimal class schedules each semester, and possible logjams towards the end of Duke students' careers, leading to extra semesters of classes. We set out to alleviate these problems via 3 different deliverables.
First, we leverage historical course catalog data to create visualizations showcasing the distribution of classes across different time periods. Then we were given access to the complete roster data, which specifically tells us which students took what courses in a given semester. We are using this to create a course scheduling assistant for the registrar. Since we know which classes students prefer taking together, the registrar can weigh the significance of clashes between classes to determine the most optimal course schedule for students. Lastly, we created a schedule planner for students who could visualize how likely 2 or more classes will collide. This provides students the complete information and foresight to draft the optimal future course plan.
In the following few slides, we present some visualizations we created. The first of which is a heat map showing the frequency of courses scheduled through days of the week and times throughout each day. As you can see, certain slots clearly have more overlap than others, making this a basic yet effective way to display course data. Next, we needed a way to figure out a good metric to determine how much a class clashed with another. We used the naive approach of class correlations. That is, given one class, what was the probability a student took the same class in the same semester? We then compared those class correlations and various manipulations of those class correlations to ground truth by using some clustering algorithms shown in the next few slides based on general subsets of the complete historical roster data. By using clustering algorithms, we wanted to validate how accurate our metrics are. Specifically, we expect the number of clusters to roughly correspond to the number of majors in our dataset, but not exactly. Our initial class correlations ended up being a high-dimensional dataset, so we reduced the dimensionality and plotted it using the algorithm t-SNE, or t-stochastic neighbors embedding. We then ran clustering algorithms on these outputs. On the left is the results of a k-means algorithm we ran on the output of t-SNE on the correlations of classes in the biology, chemistry, and psychology departments, determining the potential overlap of students that took similar courses. K-means algorithm is an iterative algorithm that tries to partition the dataset into distinct, non-overlapping subgroups where each data point belongs to only one group. To determine the optimal number of clusters, the elbow method is one of the most popular methods to determine this value. While we fine-tune our metric, the fact that k-means worked optimally with 3 clusters indicates that our data does somewhat accurately capture the underlying inherent groupings of these classes. Furthermore, the noise in this data also seems to suggest that there is more overlap between these courses, which makes sense given the interrelatedness of biology, chemistry, and psychology.
We also ran dbScan on our t-SNE graphs. This graph isn't shown here, but running dbScan on our base correlations resulted in 3 clusters yet again for our pre-med courses. What you do see on this slide are the results of dbScan on our correlations squared and cubed, which penalizes lower sparse correlations. Even in this case, dbScan managed to intuitively figure out 3 clusters as well for the squared correlations, although the cube correlations only result in 1 cluster, indicating that this metric was not ideal. What's important to note here is that, although the labels aren't shown here, the 3 clusters did not perfectly cover the departments in the squared correlations, instead grouping many advanced chem classes together and roughly creating 2 groups of pre-med and non-pre-med classes in these departments, showing overlap between these departments' courses. However, these results seem to not completely capture the information we wanted, as the clusters have a lot of noise. Furthermore, when we ran dbScan on CS, math, and stats classes, we got similar results, reinforcing this previous conclusion.
Thus, we tried an alternate approach to determine course correlations. This approach uses only the historical catalog data and used the various Trinity codes to generate a heuristic. This accounted for the course numbers denoting how advanced a particular class is, relative position among other courses in the same department, other departments a class is cross-registered in, and overall areas of study the class belongs to. Other general education requirements were also incorporated. Iterating through allows us to build a prototype which accounts for what other classes a student taking a given class is also likely to take, whether it accounts for a major or fulfills general education requirements. The final output from here is a matrix data estimating the degree of correlation between pairs of classes. This enables us to determine clusters of courses.
Moving forward, we want to combine our transformed correlations with our heuristic model into one metric. Then, given a schedule of classes, we would integrate this metric into the course time overlaps to not only determine how many people are clashing, but also weigh how important these clashes are.
Moving towards the student side planner, many Duke students like planning ahead with their Duke course plan, allocating certain major requirements or TRECs to take together. For these students, it would be extremely annoying to see these courses offered concurrently or not offered at all. Our student side planner helps students devise more educated course plans. Here is a walkthrough of what this would look like. Students have the option to either choose any 2 courses to compare or input the current 1-year teacher course plan. In the former, let's say a rising sophomore is deciding when to take BME 302 and BME 244. Given that BME 302 is only offered in the spring, the student decides to take BME 244, then BME 302, not the other way around, which would lead to the student waiting another year to take BME 302. A student can also input a sample course schedule for his or her coming school year. In our example, the first semester shows conflicts between many common CS courses, notably ComSci 230, ComSci 250, ComSci 270, ComSci 310, and ComSci 308. The second semester shows conflicts in a typical first-year pre-med course schedule, which would be Chem 101, Biology 202, Psychology 106, and Psychology 101. As you can see, some courses have a slight chance of conflicting for the CS courses, but the largest is between CS 308 and CS 270, so a student would want to ensure their course plan has these courses slotted for different semesters. For our pre-med courses, the psychology classes had major conflicts with one another, while the chemistry and biology classes had their separate conflict issues. A first-year student may want to take Chem 101 and Psychology 101 in their first semester, and Biology 202 and Psychology 106 in their second semester.
Further steps we want to take include potentially implementing the student side planner as a feature on Duke Hub for students to easily leverage. For the registrar-side planner, we hope to leverage various machine learning techniques, such as different types of clustering, or even a neural network type architecture, to go beyond providing visualizations that aid the registrar in scheduling to giving recommendations on how the registrar can improve their course schedule more optimally. Some interesting applications for this project's future include a streamlined course board, which is a dashboard that students can use to see their overall course plan over 4 years, and that registrar can continually update term by term to display course availability and timings. This could also help optimize scheduling, feeding in historical course data into a recommender machine learning algorithm that predicts potential course conflicts for given times and for given students. Our team aspires to make this platform universal, where universities around the world can customize their course board for their respective registrar and course scheduling teams.